In this video lecture, I am going to explain equivalence relation, partial order relation and composition of relation. So first topic is equivalence relation. So what is equivalence relation? Which is reflexive, symmetric and transitive. So last in my previous video of relation, I had explained the properties of relations. So reflexive, irreflexive, symmetric, asymmetric, antisymmetric, transitive. So all that properties I have explained. So now relation will be equivalence if it is all reflexive, symmetric and transitive, and it will be partial order relation if it is reflexive, antisymmetric and transitive. So let's take an example. Suppose A is a relation, A is a set and R is a relation on set A. So that means the relation will be a subset of A cross A, and this is the relation defined here. So this relation is written in terms of ordered pair. So now we have to check it should be reflexive. So for reflexive we will just see 1 1 2 2 and 3 3 ordered pair should be present in the relation. So 1 1 2 2 and 3 3 is present in the relation, so it is reflexive. Now symmetric, whenever I have AB I should have BA, means I have 1 1 I should have 1 1, the reverse of 1 1 is 1 1 only. 1 2 I have, so I should have 2 1, it is there. 1 3 I have, I should have 3 1, it is there. Then 2 3 I have, I should have 3 2, it is there. And then this 3 3 and 2 2, anyway the reverse of the 2 2 and 3 3 will be 2 2 and 3 3 only. So it is symmetric also. Transitive says if AB and BC is there, then AC should be there. So suppose if I say this ordered pair, so this is A, this is B. So 1 1 is there and 1 2 is there. So 1 2 should be there. That is AC. So 1 2 is present. Likewise, for all the ordered pair, the transitive property is also satisfied. So it is reflexive, symmetric and transitive. So that means the given relation is an equivalence relation. Now partial order relation, if it is reflexive, antisymmetric and transitive. So these relation, if I say less than or equal to, it is reflexive also, antisymmetric and transitive. How? Because if I say less than or equal to, any set is less than or equal to itself. Yes, it is true. So it is reflexive. Antisymmetric, what is antisymmetric property? If I say A is related to B and B is related to A, means AB and BA both ordered pair are there, then A is equal to B. So if I say A is less than or equal to B and B is less than or equal to A, so obviously if both the conditions are true, then that means A is equal to B. So it is antisymmetric. Transitive, if I say A is less than or equal to B and B is less than or equal to C, so definitely A will be less than or equal to C. So transitive property also holds. So it is it is partial order. Now same way we can check for subset relation and divide relation on n plus. So what is this n plus? It is set of positive natural number. Okay, and here Z means it is a set of all integers, set of integers. Okay, then next topic is operations on relation. So operations on relation, here I have like set, we have union and union of two sets, intersection of two sets. Likewise we have for relation also. So if I say I have two relations R1 and R2, so what will be the union of R1 and R2? I am going to write all the ordered pair AB, which is either in R1 or in R2. Okay, so that is union. The same way if I say A is 1 2 3 4 5 and B is equal to 6 7 8 9 10. So what will be A union B? I am going to write all those elements which either belongs to the set A or set B. So I am going to write in A union B 1 2 3 4 5 6 7 8 9 10, because 1 to 5 belongs to the set A. It doesn't belong to B, but it belongs to set A, so I am going to take that. And 6 to 10 it belongs to B. It doesn't belong to A, but I am going to take it because it belongs to the one of the set. So the same way in union also I am going to take all those ordered pair AB which either belongs to R1 or R2. Then intersection, I have to take the common element, means I have to take all those only those ordered pair which belongs to both the set. Means if I say A is equal to 1 2 3 4 5 and B is equal to 5 6 7 8 9 10. So A intersection B, only 5 is common, so I am going to write only 5. 1 2 3 4 I cannot write because it belongs to A but it doesn't belong to B. Then 6 7 8 9 10 I cannot write because it only belongs to B, it doesn't belong to A. Only 5 is the common element. So same way ordered pair, I have to take only those ordered pair which is common in both the relation. So here the order of the relation is immaterial, that is one important point regarding these two operations. Now the third operation is difference of two relation. So if I say I have two relations R1 and R2, so R1 minus R2 means I'm going to write all those ordered pair which only belongs to R1 but it does not belongs to R2. Okay, and here R1 minus R2 will be different from R2 minus R1 because R1 minus R2 will be the set of ordered pair which belongs to R1 but doesn't belong to R2, whereas R2 minus R1 will be the set of ordered pair which belongs to R2 but doesn't belong to R1. So that means I'm going to get different set of ordered pair, so both are not same. Now inverse relation means if I have AB in R, so inverse I am going to write BA. So that is my inverse relation. Okay. Then next is composition of relation. So if I say I have three sets A, B and C, and if R is a relation from set A to B and S is a relation from B to C, then the composition relation, or it is also called as SOR, so that relation is a relation from A to C. Okay, so here a relation can be defined on a set A. It can always be decomposed with itself. That means if I say what is ROR, that is nothing but R square. ROR means R cube, and ROR to the power, I mean up to n, it is R power n. So let's take one example and it will be clear. So here composition of relation in matrix form. See, either what I can do if it is given in terms of ordered pair. So if I have means I have two relations. Suppose let's take this example, then I'll come to the matrix form. Suppose this example is given. So A is my set. A is a set which has two elements A and B. B has three elements 0, 1 and 2, and C is having two elements X and Y. Okay, and R is a relation from A to B and S is a relation from B to C. So SOR will be the relation from A to C. Okay, the composition relation. So here R is also given, the relation is given, S also is given. Now I have to take the composition means from A to C. So how I have to check? See, A 0 is there. Now 0x is there. So that means this is AB ordered pair and this is BC ordered pair. So AB A0 is there and 0x is there. So I am going to write AX in composition. Similarly, A2 is there and 2y is there, so I am going to write AY. B1 is there and 1y is there, so I am going to write BY. So like that I can write directly also, or another way of solving the problem is using matrix. So matrix, if I say means obviously if I have R and S, I can write the corresponding matrix form that we have seen in the beginning only. The relation can be represented in three ways, in terms of ordered pair, in terms of matrix, and using the digraph also. So if I have R, I can write the corresponding matrix MR for that. If I have S, I can write the corresponding matrix MS for that. So R relation is a relation from A to B. So that means the order of the matrix will be 2 cross 3, means the first element will tell how many rows I am going to have in my matrix, and the second set will tell how many columns I am going to have in my matrix. So first set is having 2 elements, so the order is 2 by 3 because the second element is having 3 elements. So if first element is having 2 elements, so I am going to have 2 rows. Second element is second set is having 3 elements, so I am going to have 3 columns. And whichever ordered pair is present in the relation, for that I am going to put 1, otherwise 0. So this 2 rows represent AB and these 3 columns represent 0, 1, 2. So here I will check. This is A0, A1, A2. This is B0, B1 and B2. So A0 is there and A2 is there, but A1 is not there, so I am going to put 0 for that. Remaining 2 I am going to put 1. For B only 1 is there, so here I am going to put 1. B0 and B2 is not present, I am going to put 0. Same way I can write for S also. Now if I have to find the composition, I have to take the I have to find the matrix multiplication MR into MS. So now here we know that whatever matrix we are whatever relation is given, if I am writing the corresponding matrix for that, it is Boolean matrix. Boolean means if ordered pair is present, I am going to put 1. If ordered pair is not present, I am going to put 0. So here the matrix operation, how it will be? So this you have to remember, 0 plus 0, I am going to, it will be 0, 1 plus 0 or 0 plus 1, it is 1, and 1 plus 1, it is 1 only. 0 into 0 is 0, 1 into 0 and 0 into 1 both are 0, and 1 into 1 is equal to 1. So this operation you have to remember, same you can apply here. Now MR and MS, if I multiply it, see, now the composition relation means some SOR matrix, so that means I have to multiply both the matrix. So now here you know how the matrix multiplication happens. So the matrix multiplication, first row I am going to multiply with the first column. So first row means 1 into 1 plus 0 into 0 plus 1 into 0. So that I have written 1 into 1 is 1 only, 0 into 0 is 0, and 1 into 0 is again 0, and 1 plus 0 will be 1 only. Same way I can the first row and second column I am going to get this, then the second row and first column I am going to get this, then the second row and the second column I am going to get this. So this is what I got after multiplying. Now if I have a matrix multiply, and so see, I told you if R is a relation from A to B, S is a relation from B to C, then SOR is a relation from A to C. So this is 2 cross 2 because order of A is also 2 and order of C is also 2. So that is definitely my whatever result I am going to get, that will be 2 cross 2 matrix. So first means the row represent AB and this column represent the element of the set C XY. So here this is AX and AY. This is BX and BY. So AX and AY is present, so I am going to write that ordered pair, and BY is present, so I am going to write that, but BX is not present because it is 0 here, so that will not come. So if I know the matrix, I can then write the corresponding ordered pair representation also. So that's all about the equivalence relation, partial order, and then operation and this composition of relation. Thank you.